first thing to have floating point hardware on it. Okay, this is in the 50s with vacuum tubes, right? So we're talking old school. And they introduced this idea of an exponent bias for precisely the reason I mentioned. Makes telling which numbers are bigger, or which exponents are bigger, much easier. Okay, so that's how they're stored. And of course, if we can do it in 32 bits, we can also do it in 64 bits. Okay, it's just more bits. Okay, so in this case, we have 11 bits for the exponent, 1 bit for the sign, as usual, and then the remaining bits are for the mantissa. Okay, does that surprise you that it only goes up to 11 bits for the exponent? Right? Yeah, but that's the convention. Now, so there, and this is the thing I like about Evan's page, is when you first load it, by default, the example he gives you is the number pi, okay, which of course you can never finish writing the decimal point, I mean the expansion for it. Although there was that funny time that Indiana tried to legislate that pi was equal to 3, right? You'd think that there would be something, yes. Like, that's the kind of crap you expect out of Alabama. Okay.
Why?
Huh?
And why they try to do this?
It's a longer story. Basically, there was this crackpot. This is what we call people who think that they know mathematics, but actually are just like idiots.
Mm-hmm.
He had claimed to discover a whole bunch of things, and one of the implications of them was that pi would be anywhere from 3 or 3.2. It depended on where in his working book. And what he wanted to do was get the state legislature to pass, or state assembly, to pass a law basically acknowledging him as the discoverer of these amazing things. And in exchange, he would allow these amazing things to be taught in Indiana public schools without royalties. Fortunately, the day the bill was going to be taken up by the assembly, a mathematician just so happened to be there and read it and was like, "So, mathematician, what do you think?" He's like, "It's not worth the paper it's printed on." Yes. Oh, that's right, you were talking. All right, get out of here. Yes, okay, so. So anyway, there's pi to however many digits there are, okay? That's the maximum precision that you can get pi as a 64-bit floating point number, okay? Does that look all that precise? I don't know, that's kind of a judgment call. What do you guys think? I mean, definitely a lot better than 3.14.
Still
Okay.
not rocket science.
Huh?
Still not precise enough for rocket science.
Ah, there's the question. Is this precise enough for rocket science? Yes, it is. Okay. This is precise enough for rocket science. In fact, this gives you, NASA uses this in interplanetary computations. Okay, they do it in 64 bits. And the precision is enough to have you within about an inch if you go out to the distance from here to Pluto. Now, I would think you guys would agree that going all that way and only being off by an inch is pretty damn good. Yeah. So, yes, and I actually asked this question, or somebody asked this question a few years ago when I was teaching CS101, like, well, how precise does NASA do it? It's like, I actually don't know. So I went and Googled and found a really fantastic article about precisely this question. And yeah, so that's interesting. So yeah, 64 bits is actually good enough for NASA for the most part.
How many years ago was this?
A couple of years ago. I mean, was it? It was pre-COVID, so it might as well have been 10,000 years ago.
Yeah,
probably need to have a little bit more precision and do 128-bit, but yeah, that's not the end of the world. Okay. All right, good. Question, preguntas, fragens? Yes.
Is there anything that 64 bits is not precise enough for?
Good question. Yes. So if you're trying to do like, I don't know, like some really exotic like nuclear chemistry or like really tiny stuff like modeling atoms and whatnot, then maybe not. Or you're trying to simulate like the evolution of the universe or a galaxy, right? Something like that. The Matrix, 64 bits won't be good enough for the Matrix.
So when we start doing 128 bits, things will get better.
Then we might get matrixy, and there may be somebody in a red dress walking in. I don't know. We'll find out, right? Has anybody seen? When does the new movie come out? Yeah. Mm-hmm.
For the 2 to the power thing, basically every number has to be big. It starts with 127 and just goes for the exponential.
Yes. Okay, so I think the stream is back up. So sorry. Won't die again. But if it does, then c'est la vie. Okay. Huh? Maybe about 10 minutes ago. Yeah. Okay. So anyway, so the last bit for at least right this instant is, well, this is how we store the floating point numbers. This is the format. But how do we actually program with these things? Right? So let me make a new file here, and let's say, okay, so oops, not downloads, we want documents, examples, and I'll make a new folder for, say, floats. Oops. Okay, so if I'm going to do something here, okay, how do I do floating point stuff in C? Okay, well, actually, you guys kind of already saw a little bit of that when we did the triangle struct problem, right? So I could say float A equals 3.14 and double B equals 6.02. I'm just making up numbers. Okay, so a float is a 32-bit number, and a double is a 64-bit number. So it's double the precision, not really exactly double, but that's just what we call it. It's a double precision number, okay? All right, so those are the two types of floating point numbers that you can work with, okay? And then let's say I wanted to print the sum of these two things. Well, what's the problem with them if I try to add them? Yeah, they're different data types, okay? So I can't just add a float and a double because one of them is 32-bit and the other 64-bit. So it's the same problem as integers. Okay, so let me just make them both doubles just for sake of example for right now. And I could say something like that, and then I would pass it A, B, and A plus B. Okay? Now, this part you guys are going to be a little bit annoyed with. Printf, the format string for a floating point print is %f, 32-bit or 64-bit. It's the same. Asterisk, and I'll show you what the asterisk is here in a moment. Okay, so, and then we, of course, return 0. Okay, all right, so let's run this. Oops. Oh, yeah. Okay, whatever. Now, you notice that how did printf output this thing? Yeah, it did put extra zeros in there, and its default is to do 6 decimal points. You can change that. I don't remember the exact command to do it, but you change it in the format string, the %f thing, you put some extra stuff there, and you can control how many decimal digits come out.
Whatever you put after a dot, right?
Yeah, there's a dot. And anyway, just you look that up because who cares? Well, I mean, we care, but I don't remember it. All right, so that's the convention, right, is 6 decimal places. You can change that to increase or decrease it as relevant for whatever purposes you care about. Okay, so that's great. But what I want to really start to point out here, of course, is that's how we do it in C. But C hides a lot of stuff from us because these numbers, the 3.14 and the 6.02 and the sum, right? Where do those things exist actually, like to do this addition? Well, if I gave you 2 integers and I said to add them, where do they need to be and how do you add them? In assembly. Yeah, you got to put them into 2 registers and you got to add them together and say, all right, I want the answer to go in whatever other register, and then I need to print them, so I need to put them in appropriate registers for the printing so that I follow the calling convention. And all of that stuff has to be the same, right? Is any of that different with floating point? Theoretically. Well, yes and no. It's not different in the sense that where do numbers need to go to do arithmetic on them? You got to go to a register. What's different, though, is which registers. Okay, the X and the W registers are only for integers. X and W. No, it's not R. There is no R. Yes, there are things, there are R's in, actually no, on Intel, the R's are integer only too. Okay, there's a completely separate set of floating point registers, okay, that have different names. And the names for them are S, D, and you can guess what the S and the D stand for. Single and double, okay? And they're related the exact same way that X and W's are, okay? So D0, for example, has 64 bits. S0 is the lower 32-bit half of it, okay? So they're really the same register in a hardware sense, but it's just sort of, you're only looking at half of it, okay? All right, so is that part okay? And there are a luxurious 32 of these things. So you can go from D0 all the way up to D31. And this is even nicer. Are there any ones that you're not allowed to use? Okay, in the general integer ones, were you allowed to use number 18, number 29, or number 30? Or number 31 for that matter? No, those were reserved for specialized purposes. Okay, like keeping track of the frame pointer and the link register and so on. Okay, so those were special and you weren't allowed to use them unless you were using those special purposes. The rest of them were okay, with the exception, of course, that what happens is 0 through 7 and so on. Are functions obligated to preserve these things? No. Okay, that's also true about the floating point ones. Okay, is that they're not obligated to be preserved. So, we need to basically, most of the instructions we've talked about, okay, move, load, and so on, addition, all of those things have floating point equivalents of them that operate on the floating point registers. So in the same way that we have add for addition, we have fadd for floating point addition. Make sense? Okay. And there's also fmove, although that one is going to cause some headache, as you guys will see. Right, so there are a lot of these floating point operations that go with the integer ones. Okay, there are also operations for what happens if you have an integer and you want to turn it into a floating point number. Let's say you have the integer 2 and you want to turn it into the floating point number 2.0. There is an operation to do that, and there's another operation that goes the opposite direction. If I take a floating point number and I turn it into an integer, what am I essentially having to do? Right, if I take 3.14 and spit 3 out, what have I basically done? Huh? I'm sorry, I can't hear you. What about it? Yeah, I've had to round it somehow, right? Yeah, and the convention, right, there's convention about the rounding properties, right? And, you know, maybe I would need to round the number for some reason. I don't know. Yes.
Is there a way to separate the numbers? Let's say anything up before, after the decimal point, and before the decimal point into separate registers.
Yes, but you'd be doing bit banging. So, you know, extracting bits and putting them in separate places. Okay, so Fardeen's question actually is, that is a system called fixed point. Okay, so what you could do, and this is a valid system, is store all the crap before the decimal point as an integer and store all the crap after the decimal point as an integer. And sort of make a number out of 2 chunks, right? That is a system, it's called fixed point. But yeah, I mean, we really don't use it anymore because the floating point hardware is so fast nowadays that who cares? Okay. Okay, so let's take our silly little program here and let's actually have the compiler spit out the assembly. Okay, so you guys remember when we did this back at the very beginning, take machine produced assembly? Well, let's look at the machine produced assembly for this guy, shall we? Okay. Well, we got our format string, we got our main function. It's doing some stacky stuff, okay? It's defining here some words. Okay, now I should be clear that these things are the numbers. Okay, the pi and whatnot, but it's sort of like if I encode them in my 32 or 64, actually in this case, 64-bit floating point. Right? I have a 64-bit number. If I temporarily pretend that that number is an integer, what number is it? Well, whatever, and I write that down here. I could also actually put this in hex, which is more useful, because let's say that I needed to know 3.14, right? And I could sit down and calculate by hand what all the bits should be, and then therefore what the expression should be in hexadecimal, or I could just use that handy float toy thing, right, which outputs in hex. So yeah. Okay, so anyway, there it's just predefined the numbers. Okay, and right, what's interesting here is it's actually done the arithmetic beforehand, but, well, sort of. Okay, so here's what it's done, right? These 2 instructions, right? It's taken this data and put it in memory on the stack. Okay, that's all that crap that's going up above there. Okay, but if I want to do addition, I need to load these things into registers. Well, what registers is it loading the 2 numbers into? So that's the highlighted part. Yeah, D1 and D0. Okay, and where did those numbers come from? Well, they were on the stack someplace. And so the stuff after it is just saying, okay, the D1 thing was 24 bytes up from the stack pointer, and the other guy was 16 bytes up from the stack pointer. That's where they were located in memory. Okay, great. So now my 2 numbers are sitting in D0 and D1, And can I add them? Yeah. Well, they're floating point, and so that's why I have the command fadd instead of just add. And the syntax here is exactly the same. I need to do 0 and 1, those two registers, add them together and put the answer in D0. Well, okay, that's cool. Okay, then I need to print them. Okay, if I want to print something, what's got to go in X0? The address of the format string. Okay, our format string in this case was the sum of float and float is float, right? So what's the convention then? If the X0 gets our register, or sorry, excuse me, the format string's address, then the parameters have to go in order. What's our first parameter that we pass? Whatever the first float was, yeah? So where does that have to go? In integer land, we would have to put it in X1, right? Because X0 is already occupied. But we're in floating point land for that number, so where do we put it? D0, because D0 has not been used for something already. So they go in order, okay? And they go in order, like let's say that I wanted to print an integer and a float, okay? What would I have to put in X0? All right, so let's say that my format string was something like %law_i %f. X0 would have what? The address of the format string. Okay, so this thing, okay, with words if I wanted to put them there. All right, what would X1 have in it? The int. And what would D0 have in it? The float. Okay, let's spice this up. Oops. Let's throw in another integer. Where would this guy go? Tricked you, right? So this would be X1, D0, W2. Where would this one go? D1. Ah, and you guys thought this was bad with just integers. Yeah? It's all good. Okay. All right, so the calling convention, though, for functions involving floats is the exact same as if with ints, right? Anyway, all right. Have a fantastic Thanksgiving break. Sorry about the stream quitting today because I'm an idiot. And stay tuned for things on Canvas. See you guys later.